Hello everyone, for this tutorial video, I'd like to explain how you can add smaller and smaller areas under a curve in order to approximate a definite integral. If we assume a function of x is continuous on the interval from a to b, then it follows we can determine the area under it by bubbling in all of the space between the x-axis and the curve given by the function. What we would like to do is show algebraically/geometrically that you can get this area exactly by dividing it into smaller and smaller rectangles. We first state that the change in x, or the length of each rectangle, must be b minus a divided by number of rectangles. If we use the function on the right end of each interval as the height of the rectangle, we see we overestimate the area under the curve. And in particular, we can get the exact area these rectangles make up by adding 1/2 times the function at the end of each interval times the length of each interval, which is given by change in x. In the case of the function we are working with right now, the total area is 5.75. If we use the left end as the height instead, we see we underestimate the actual area, and in particular, this area would be 3.75. If we instead use the function at the midpoint of each interval to dictate the height of each rectangle, we see we get much closer than either of the other two to the actual area. And the area using the midpoints is 4.625. Using a computer program, we can see the actual area is 14/3 for comparison purposes. If we next do all these tests again, but with more rectangles, so a smaller length for each rectangle, we can see that all of our estimations get closer to the actual area, as we could probably predict. So in conclusion, the general process for any function is to use the formula for change in x, which is b minus a over a number of rectangles. Assume each rectangle must be equal length in order to get a more convenient formula for the sum, which will be x sub 0 equals the left endpoint a, x sub 1 equals a plus change in x sub 2 equals a plus 2 change in x, and so on. So x sub n must be a plus n times change in x. And next, we choose an arbitrary point in each interval to dictate the height of the rectangle. We see the area is then approximately the function at this arbitrary point times the change in x for each interval. We can condense this using summation notation, which is I equals 1 for the beginning of the sum, n for the number of terms in the sum, and function at arbitrary point in the interval times length of interval. The sum is so important that it has a specific name, which is Riemann sum, spelt with 2 n's rather than 1 as you might initially expect, as a reference to the mathematician who first discovered this sum. We can state that the area is exact in an approximation as the number of terms in the sum approaches infinity. And here we have the literal definition of the definite integral. Now that we have shown why the definition of the definite integral is the way it is, we can move on to using this literal definition to prove integrals of specific functions, like what we did for derivatives earlier. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.